We are going to do an example. I promise I haven't forgotten, but I want to talk about this idea that I mentioned, that there might be more than one correct model. Because of that multicollinearity, several variables might do a good job. The way you beat the issue of multicollinearity is model selection. How do I know which variables to use? The method I'm going to show you, and the method we emphasize in this class, is called backwards model selection. And it's called backwards because you kind of start with everything and then you chop stuff out. There's another method called forward selection where you start with nothing and then you look at all the variables and say, if I only had this variable, which one would give me the best p-value? And you add it in, and then you do it again until you get all the variables that have significant p-values. Both of these are valid methods. I'm going to teach this one for this class because a lot of this class is exploring what variables do I need. Do I need an x1 squared? Do I need an x1 times x2? So we can throw everything in and then start taking pieces out. And a lot of times you'll end up with the same model either way. These are the variables you need in your model and everything else falls out or isn't put in. But you can imagine why you might get a different answer. Imagine a group of people working on a term project and you start picking out the people who aren't working. And who are you left with? Well, the ones who are really good at not paying attention to everybody else goofing off. On the other hand, if you started putting in the best workers one at a time, you might put the goof off in right from the very beginning because they're really good at working by themselves. And then as you add other people in until you finally get a good term project. The light turned on. There does exist a third method called best subsets, where you look at literally every possible model you could make, which naturally means whatever model you would have picked with backwards or forwards is part of best subsets, and looking at all those models, you pick whichever one you think is the best one. This method hasn't been that popular in the last 50 years because that is a huge amount of work. Can you imagine the punch cards? And you're lucky to have punch cards. Today's computers can actually do this, which is cool. I'm not going to show you because it's a little more complicated, and in the regression class they do go over this. But this is a very good method as long as you know how do you compare two different models. You're looking at two different possible models, maybe the one from backwards and the one from forwards, and you're trying to decide which one do I like. And here it's really important that you do not rely on R squared to tell you how good your model is. R squared is purely based off how much error is there in the predictions. And that might sound like a good idea, but let me give you an example. Here we have our data set here. Can you see that? The dots don't really show up. Well, if you can't see them, there are dots. And what would you do if you wanted to fit this? Well, it looks to me like a straight linear line makes sense. Y equals beta naught plus beta 1 x. And that's a good fit, but then we have this competing model, the blue line. And notice that blue line hits every single dot. How much error is there in the prediction? 0. Our blue line actually hit all the dots. The red line, no. The dots kind of were bouncing around the line. So you might think the blue line is better. But look at the equation. How do you get a line that bends and hits every single dot? Well, you've got to do like an x to the 20th polynomial. That's a lot of terms. Does it seem like the blue line is actually doing a better job of showing the relationship between x and y than the red line? The answer is no. The red line was the truth, and there's just this much error. The blue line has no error because you've overfit the data. You have fished and found a pattern which really wasn't a pattern at all. And you have all these terms which are useless. You really only needed a linear term. So R squared would be 100% for the blue line, which sounds great. For the red line, it would be around 80%, 0.8. So if you only go off R squared, you are always going to end up picking a model which has more terms and is more complex and has useless junk in it. So what can we do instead? It's not how well it can predict. It's going to be some adjusted form, which is why R squared adjusted is one of the things that R naturally spits out. R squared adjusted says if your predictability is improved, it needs to improve based off how many terms you have. If you have 20 terms in the model, you better have 20 times better predictability. And in this case, it wouldn't be. So the R squared adjusted would penalize this blue model, and it would drop from 100% down to probably 10% or something super tiny to tell you you've got a lot of extra junk in there. You're fitting patterns that aren't really there. R-squared adjusted isn't the only one. There's a lot of others that we're not going to talk about in this class, but that you'll hear about if you take the regression class. These are called information criterions. A. Keiki made one, and so it's named after him. This is a Bayesian information criterion, and we have the deviance information criterion. Lots of different ways of saying, if my model is bigger, my predictability should be a lot better. I'm not just asking whether the predictability is small. So you can see why setting your alpha really plays a big role in what kind of model you end up with. If your alpha is a little higher, then there's going to be terms in your model that maybe had a p-value of 0.07, and you'll say, oh, my alpha is bigger, I'm going to leave those in. You'll have more terms. Why is that good? Well, more terms means you have more movability in your line. You'll be able to fit the data better. You'll have a lower S, better predictability, better R squared. Of course, it's also a little more complex to explain. If you have a lower alpha, fewer terms in your model, because there might be terms that had a p-value of 0.02, and you'll say, well, I've dropped my alpha, I'm going to toss that guy out. It's a simpler model and easier to explain. And which direction you go often depends on where you are in your research. These kinds of situations happen for exploratory studies. We don't know what's out there. We're measuring tons and tons and tons of variables. There's a lot of error and confusion, but we're going to find something interesting, and we're going to use that to apply for a grant, get money, and study it further. You would do this. Put in more terms. Is there anything that might be interesting? Psychologists, for example, will do this. Lots and lots of terms. Years later, somebody might say, you know what, that turned out to not really be important, but at the beginning, you don't know. So you put more in your model, and you get good predictability, and you slowly understand those as you do more research. After you think you know what's really working, these are usually what you'll use for confirmatory studies. I really believe these variables are making an effect. So you drop your alpha and say, if it turns out that you're still a little iffy, I'm going to throw them out, because by the time I'm done, I'm going to say, we know what these variables do. So exploratory at the beginning, get grants, do more research. Confirmatory, finally we have answers published in some of those big magazines. Next video, let's start looking at that example that I think I promised you earlier.